Consider the force that has never once let go of you. Gravity has been holding you down every second of your life, through every step, every fall, every night you have ever slept. It feels like the strongest thing in the world when you trip on a stair, and yet here is the fact that should stop you cold. A cheap refrigerator magnet, the kind that holds a photo to your kitchen door, can lift a steel paperclip clean off the ground, and in that instant it is overpowering the gravitational pull of the entire planet Earth, the whole mass of the world, 6 sextillion tons of rock and iron and ocean, pulling down on that one paperclip. And a magnet you could close your fist around wins. That is not a trick. Gravity really is that weak. Measured against the electromagnetic force, gravity is somewhere between 10 trillion and 100 million trillion times feebler, depending on which particles you compare. Write that number out and it has 36 to 47 zeros. So before you go any further, if you find this strange, and it is strange, consider subscribing and leaving a like, so more of these quiet deep dives can find you. You can also listen to the whole thing on Spotify when you would rather close your eyes. That is the only thing this video will ask of you. Now let the rest unfold. Here is the puzzle at the center of everything you are about to hear. The one force you feel most, the one that pins you to your bed right now, is by an enormous margin the weakest force in the universe, and it is also the least understood. We have measured the others down to exquisite precision. We have named the particles that carry them. Gravity has slipped through every net we have ever built. Start where nearly everyone starts, because for 200 years this was the whole story. In 1687, Isaac Newton published a book with a long Latin title, usually shortened to the Principia. Inside it was a single equation that changed how the human race saw the sky. Newton wrote that every mass in the universe pulls on every other mass. The strength of that pull depends on how heavy the two objects are and on how far apart they sit. The formula is short. Force equals a constant, called big G, times the first mass times the second mass, divided by the distance between them squared. That last part matters more than it looks. Distance squared means the pull drops off fast. Move twice as far from something, and its grip on you falls to a quarter. Move 10 times as far, and it falls to 100th. But it never truly reaches zero. This is the quiet, staggering claim buried in Newton's math. Gravity has infinite range. Every star you can see tonight is tugging on your body right now by an amount too small to feel, but never actually nothing. Newton's law worked beautifully. It explained why apples fall and why the moon does not fly away. It predicted the orbits of the planets. It let sailors cross oceans and, much later, let engineers land probes on distant worlds. For 220 years it was as close to perfect as any idea humans had ever produced. Newton had done something almost unbelievable. He had written down the rule that the heavens obey. But there was a crack in it, and Newton knew. His equation described what gravity does with astonishing accuracy. It said nothing at all about what gravity is. Why should two lumps of matter, separated by the cold emptiness of space, feel each other at all. There is nothing between the earth and the moon but vacuum. No rope, no rod, no visible thread. And yet the pull is there, steady and exact. Worse than that was the timing. In Newton's math, the pull is instant. If the sun vanished this second, Newton's equation says the Earth would feel it let go this second and fly off into the dark immediately. The force reaches across 93 million miles with no delay whatsoever. Newton himself found this idea troubling. He called action at a distance an absurdity and admitted he could not explain the cause. He had given the world a law it could trust and confessed he did not know why it was true. For 2 centuries that gap simply sat there. Then physics learned something Newton could not have known. Nothing in the universe travels instantly. There is a speed limit, and it is the speed of light, about 670 million miles per hour. No signal, no push, no information of any kind can cross space faster than that. Which meant Newton's instant gravity was not just mysterious, it was impossible. If the sun disappeared, its pull could not vanish everywhere at once. The news would have to travel, and travel takes time. The person who closed that gap was Albert Einstein, and the way he did it did not tweak Newton's picture. It threw the whole picture out. In 1915, after nearly a decade of work, Einstein published the theory we call general relativity. And its central idea is so strange that people still struggle to hold it in their heads more than a century later. Einstein said gravity is not a force reaching across empty space at all. There is no pull. There is no invisible hand. Instead, Einstein said, space and time are not an empty stage. They are a single flexible thing, woven together, that physicists call spacetime, and matter bends it. Any object with mass presses a dent into the fabric of space-time around it. The heavier the object, the deeper the dent. The sun sits in a deep well of its own making. The earth sits in a shallower one. You, right now, are pressing the faintest possible dimple into the geometry of the universe just by existing. And here is the part that replaces the pull. Objects moving through this bent space-time are not being tugged. They are simply following the straightest available path through a landscape that is no longer flat. Physicists have a word for that straightest possible path through curved space. They call it a geodesic. The Earth is not being yanked toward the sun by some cosmic string. The Earth is coasting in a straight line, as straight as it can manage through space that the sun has curved into a bowl. There is an old image that helps, and it is worth holding on to as you lie there. Picture a large rubber sheet pulled tight and held flat. That is empty space-time with nothing in it. Now set a heavy bowling ball down in the middle. That is a star. The sheet sags into a deep curved well around the ball. Nothing has been pulled, but the shape of the whole surface has changed. Now roll a small marble across the sheet nearby. It curves toward the ball. Not because the ball reached out and grabbed it, but because the surface it is rolling on is no longer level. Let the marble go at just the right speed, and it will not fall in. It will circle the inside slope of the well, going around and around the way a coin spins in one of these charity funnels before it drops. That circling marble is a planet. That is what an orbit really is in Einstein's universe. Not a tug of war between two masses, but a small thing rolling forever around the curved slope carved by a larger one. The moon circles the Earth's dent. The Earth circles the sun's. The sun itself circles the vast dent at the center of our galaxy. This is the idea that sets gravity apart from everything else in physics, and it is worth saying slowly. Every other force we know works by exchanging something. When two magnets push apart, particles of light, photons, are passing between them. The forces inside an atom's nucleus work the same way, by trading particles back and forth. Push, pull, attract, repel. All of it is carried by some tiny messenger crossing this gap. But gravity, in Einstein's picture, has no messenger. Gravity is not something travelling through space. Gravity is the shape of space itself. Read that again and feel how odd it is. The reason you're held to your bed tonight may not be a force at all. It may be nothing more than the geometry of the room around you, gently bent by the huge rock beneath you. You cannot see this curvature. You cannot touch it or point to it. You can only feel it as the weight in your own limbs. You are being held down by the shape of four-dimensional space, warped by a spinning world you did not choose to stand on. When Einstein finished this theory, it was breathtaking, but it was still just math on paper. Beautiful equations have been wrong before. Einstein's idea made one prediction that Newton's could not, and it was testable. If mass really bends space, then light itself should follow the curve. A beam of starlight grazing past the sun should bend, just slightly, as it crossed the dented space near that huge mass. Newton's theory allowed almost no bending. Einstein's predicted about twice as much. The two theories gave different answers, and the sky could settle it. The problem was the sun's glare. You cannot see stars next to the sun in ordinary daylight. You need the sun blotted out. You need a total solar eclipse. In May of 1919, the British astronomer Arthur Eddington led an expedition to photograph the stars around the darkened sun during exactly such an eclipse. He measured where those stars appeared to sit, and their light had shifted, bent off its straight path by the sun's gravity by just the amount Einstein had predicted and not the amount Newton allowed. The shift was tiny. The starlight moved by less than the width of a coin seen from a mile away. But it was there, and it was real, and it matched. The photographs from that expedition look like ordinary star fields, faint dots on glass plates. Yet each of those dots was quiet proof that space is bent, that light rides the curve, that Einstein had been right. When the results were announced, Einstein became famous overnight, the first true celebrity of physics. He had shown that gravity is geometry, and the universe had agreed, and general relativity has kept agreeing for more than 100 years. Every test we have thrown at it, it has passed. It predicted that gravity would bend the light of whole galaxies, and it does. It predicted that clocks run slower, deeper in a gravity well, and they do. So exactly that your phone's navigation depends on the correction. It predicted ripples in space-time from colliding black holes, and in 2015 we finally caught one. A century of experiments, and not a single clean failure. It is one of the most successful ideas the human mind has ever produced. And yet, and this is where the wonder deepens rather than settles, it is not the final word. General relativity is flawless right up until the moment it isn't. Push it to the centre of a black hole and the equations stop giving sensible answers. They spit out infinity. The curvature becomes infinitely steep, the density infinite, and infinity in a physics equation is not an answer. It is a flare going up, a sign that the theory has reached the edge of what it can describe. The same thing happens if you run the universe backward to its very first instant, to the Big Bang. Relativity breaks, the math tears, so we are left standing in a strange place. We have a theory of gravity so accurate it steers spacecraft and predicts ripples from across the universe. And that same theory tells us, in its own language, that it cannot be the whole truth. Somewhere inside the deepest gravity wells, in the crushed hearts of black holes and in the birth of everything, a better idea must be hiding. We have not found it yet. Part of why we have not found it comes back to that opening puzzle. To build a better theory of gravity, physicists have spent 80 years trying to describe it the way they describe every other force in the language of quantum mechanics, as something made of particles. For light, they found the photon. For the forces inside the atom, they found their carriers too and measured them, and won prizes for catching them. Each of the other three fundamental forces has a messenger particle we have named and detected and can point to on a chart. Gravity has none. If it has a carrier particle, no one has ever seen it, or caught it, or measured it in any machine on Earth. It has a name already, given to it by hopeful theorists long before anyone found it. But a name is not a discovery, and this is the crack that runs under all of modern physics, the reason gravity remains the one force that will not fit the pattern. For 4 years, Einstein's strangest claims sat on paper, waiting. He had published General Relativity in 1915. It said the sun does not reach out and pull the planets toward it. Instead, its mass bends the space around it, and everything nearby simply follows that curve. It was a beautiful idea. For a while, it was only an idea. To become physics, it needed a number and a way to catch that number in the act. Einstein gave the world exactly that. He said the sun's mass should bend the path of starlight skimming past its edge. A ray of light grazing the sun would be pushed sideways by a tiny angle. And here was the part that could settle everything. Newton's older picture, treating light as if it fell like a thrown stone, also predicted a bend. But Einstein's number was twice as large. Curved geometry bent the light twice as far as a simple pull ever could. Twice. That one word was the whole experiment. If starlight bent by the smaller amount, Newton kept the universe he had ruled for 2 centuries. If it bent by the larger amount, then space itself was curved, and the world was a far stranger place than anyone had been willing to say out loud. There was only one problem, and it was a stubborn one. You cannot see the stars that sit next to the sun. The sun drowns them. Its glare floods the sky and erases every faint point of light for a wide stretch all around it. To photograph a star resting right beside the sun's edge, you first have to switch the sun off. Nature does that only rarely, for a few minutes at a time, along a narrow ribbon of shadow that falls across the earth. You need a total solar eclipse, so the test became a journey. The sun would go dark in 1919, and the band of shadow would pass far from the quiet observatories of England. A cluster of bright stars happened to sit almost directly behind the sun that day, close enough to its edge to be worth chasing. And so, Arthur Eddington, an English astronomer who had read Einstein's work and believed it deserved a real answer, helped organize expeditions to sail toward the eclipse. They packed their telescopes and their fragile glass photographic plates into crates, boarded ships, and travelled thousands of miles to stand in exactly the right spot on exactly the right day. Think about the fragility of that plan. Everything depended on a few minutes of darkness that could not be rehearsed or repeated. Clouds could ruin it. A trembling instrument could ruin it. A single bad exposure could ruin it. There was no second chance until the next eclipse, years away, somewhere else on Earth. They had one narrow window, and they had carried it across an ocean to open it. When the moon finally slid across the sun, and the sky went dim in the middle of the day, the stars that lived beside the sun came out. Eddington's expedition worked fast, exposing plate after plate while the shadow held. Then the light returned, and the crates were sealed, and the real work began. Because the measurement was never made under the eclipse itself. It was made later, in the slow comparison of two pictures. Here is the detective part, and it is quieter than you might expect. Months before the eclipse, that same patch of sky had been photographed at night, when the sun was nowhere near it. On that plate the stars sat in their true undisturbed positions, their light travelling to the camera in straight lines through empty space. On the eclipse plate the same stars were photographed again, but this time their light had passed close to the sun on its way to Earth. If Einstein was right, the light had been bent as it went by. And so those stars should appear to have shifted, nudged outward, away from the sun's edge, compared to where they truly belonged. That was the entire proof. 2 photographs of the same stars. One taken while the sun sat in the way, one taken while it did not. Lay them side by side. Measure the gap between each dot and its earlier position, and the numbers would speak. A larger shift meant curved space. A smaller shift meant the old pull. No shift at all meant light did not care about gravity, and both great theories were wrong. The trouble was the size of the shift. This was not a dramatic swing you could see with your eye. The stars did not leap across the plate. The displacement Einstein predicted was staggeringly small. A sideways nudge you can picture like this. Imagine holding a small coin at arm's length. Now walk it a full mile away and hold it up against the sky. The angle that coin covers, seen from a mile off, is roughly the scale of the shift Eddington was hunting for. Starlight had been leaned sideways by less than the width of a coin held a mile away, and his job was to measure that on a photograph the size of a dinner plate. To find something that faint, every other error had to be hunted down and subtracted. The temperature could warp the glass. The telescope could flex. The two plates might differ in scale by the smallest fraction. Eddington and his colleagues pored over the tiny dots for weeks, measuring positions, checking, comparing, ruling out every ordinary explanation for a shift, until only gravity was left to blame. It was slow, careful, unglamorous work. It was also the moment the shape of the universe was being weighed, and the faint dots answered. When the measurements were finished, the stars near the sun's edge had been pushed outward by close to the larger amount, the amount only Einstein's curved geometry allowed, not the smaller Newtonian nudge, the bigger one. The light had bent about twice as far as an old-fashioned pull could ever bend it. The plates that looked, to any casual eye, like ordinary fields of scattered stars were quietly holding the first strong evidence that mass really does bend space, and that light simply follows the bend. It is worth sitting with what that means, because it is easy to say and hard to feel. Those stars had not moved. They were exactly where they had always been, unimaginably far away, indifferent to the sun and the earth and the small people measuring plates. What had moved was the path their light took to reach us. The sun had not tugged on the light. It had reshaped the space the light travelled through, and the light, going as straight as it possibly could, had curved anyway, because straight itself was curved near all that mass. That was the turning point. Before those photographs, general relativity was an elegant argument. After them, it was a measured fact of the sky, dated and photographed and checked. Gravity was no longer safely an invisible hand reaching across empty space. It had become geometry, the literal shape of the emptiness itself, proven by starlight that arrived slightly out of place. Newton's equations still worked beautifully for falling apples and orbiting moons, and they still do. But at the edge of the sun, in front of everyone, the deeper truth had shown itself. Space bends, and things fall because they are following the bend. Once you accept that, gravity starts to look different from every other force you know. When you feel a magnet grab a nail or watch static lift a scrap of paper, there is something being exchanged, a push carried across the gap. Physicists can name the carrier and point to it, but the sun-bending starlight did not point to any carrier at all. It pointed to the shape of space. The eclipse had not caught gravity handing anything back and forth. It had caught gravity being the stage, not an actor on it. And that is the puzzle those 1919 plates left sitting on the table, the one still unsolved a century later. Everything else in the sky can be described as a field with a particle inside it, a messenger you can hunt for and eventually find. Gravity refused to fit that picture. Einstein had shown it was curvature, a property of space-time rather than a thing travelling through space-time. There was no messenger in his equations, only the warp itself. So even in triumph, even with the starlight measured and the shift confirmed, a strange gap opened underneath the victory. If gravity is geometry, what is that geometry made of, down at the smallest scale, where everything else in nature comes in tiny discrete pieces? Nobody could say. Nobody has said yet. Every other force in nature is carried by a particle you can name, and gravity so far is carried by nothing anyone has ever caught. Every other force in nature is carried by a particle you can name, and gravity so far is carried by nothing anyone has ever caught. Every other force in nature is carried by a particle you can name, and gravity so far is carried by nothing anyone has ever caught. The photon carries light and electricity. Heavy particles carry the weak force. Gluons carry the strong force that binds the heart of every atom. Each one has been seen, measured, counted. Gravity stands alone with an empty chair where its particle should sit. Physicists have already given that empty chair a name. They call the missing thing the graviton. On paper, the graviton is easy to describe. It would be massless, so it never slows down. It would be electrically neutral, so it carries no charge at all. It would move at the speed of light, about 670 million miles an hour, the same sealing everything massless obeys. And it would carry a property called spin, set at exactly 2. The photon has spin 1. That single step up, from spin 1 to spin 2, is not a small detail. It is the mathematical fingerprint of a particle that would bend space-time instead of pushing charges around. If gravity is made of anything, this is the shape that anything would take. Before we go deeper, one small thing. If these quiet walks through the strange edges of physics help you sleep, a like or a subscribe helps this channel keep making them, and you can find the same episodes on Spotify for the nights you would rather just listen. That is all. Now settle back and let us go looking for a particle no one has ever held. Here is the problem that makes the graviton so maddening. Gravity is unimaginably weak. You feel it as the weight in your body only because the entire planet, every ton of it, is pulling on you at once. A small refrigerator magnet can lift a paperclip straight off a table, and in that moment it outmuscles the gravity of the whole Earth. Depending on which particles you compare, gravity is somewhere between 10 to the 36th and 10 to the 47th times weaker than the electric force. Write that out, and it is a 1 followed by dozens of zeros. That is the gap between the force that shapes galaxies and the force you overcome every time you stand up. Now shrink the question down to a single particle. If one graviton exists and one of them just brushed against your body right now, the nudge it would give you is so faint that no instrument ever built could notice. And this is where a famous physicist named Freeman Dyson made a calculation that has haunted the field for years. Dyson asked a simple question. Could you ever build a detector sensitive enough to catch a single graviton by ordinary means? He worked through the numbers. To register one graviton reliably, a conventional detector would have to be so enormous, so densely packed with matter, that its own gravity would pull it inward. It would collapse into a black hole before it ever recorded a click. Sit with that for a moment. The instrument sensitive enough to see gravity's particle would be destroyed by gravity itself. It is as if nature built a lock and then hid the key inside a fire. For a long time, that calculation was taken almost as a verdict. Many physicists quietly concluded that a single graviton might be forever beyond reach, not because it does not exist, but because the universe will not let you look closely enough. And yet, as of now in the last year, a small team decided to try anyway. Physicists at the Stevens Institute of Technology and at Yale University have begun building the first device ever designed specifically to hunt for a graviton. It looks nothing like the giant machines you might imagine. There is no ring of magnets miles across. Instead, picture something the size of a coin, a tiny resonator, a small drum made to vibrate. They submerge it in superfluid helium, a strange liquid that flows with no friction at all, and they chill the whole thing down toward absolute zero, colder than the empty space between the stars. At that temperature, the little drum falls into what physicists call its quantum ground state. It is as still as anything in the universe can be, and in that perfect stillness, the smallest possible unit of vibration becomes visible. Physicists call that smallest unit a phonon, a single quantum of sound. The idea is this: a gravitational wave, a ripple in space-time rolling in from some distant collision, might carry gravitons. If one of those gravitons strikes the chilled drum, it could deposit exactly one phonon, one faint click, in a device built to be quieter than almost anything that has ever existed. Think about the scale of what they are trying to hear. Imagine standing in a stadium packed with a roaring crowd and trying to make out a single whisper spoken in another galaxy. That is not an exaggeration of the difficulty. That is roughly the ratio between the signal they want and the noise they must silence. Every stray vibration, every trace of warmth, every footstep in the building has to be stripped away until only the whisper could possibly remain. As of now, the detector is still being built. No graviton has ever been directly caught. The chair is still empty. But suppose it works one day. Suppose a single click comes through, cleanly, unmistakably. That would settle a question physicists have argued over for the better part of a century. Because underneath all of this sits a deeper problem, one that is not about engineering at all. It is about whether gravity is even the kind of thing that has a particle. To understand why that is in doubt, you have to know that our two best theories of reality do not get along. On one side there is quantum mechanics, which describes the world of the very small, where everything comes in discrete lumps, in particles and packets. On the other side there is Einstein's general relativity, which describes gravity not as a force with a carrier, but as the pure geometry of space-time bending under mass. For more than 80 years, physicists have tried to fold these two together, to write down a single theory where gravity behaves like the other forces, made of particles obeying quantum rules. Every attempt has run into walls. Out of that long struggle, two great rival programs emerged, and they still divide the field today. The first is string theory. It makes a bold and beautiful claim. It says that every particle you have ever heard of, the electron, the photon, all of them, is not a dot at all. Each one is a tiny vibrating string, a one-dimensional thread, and the different notes it plays are what we perceive as different particles. In string theory, one of those notes comes out with exactly the right properties to be the graviton, massless and spin 2, dropping out of the mathematics almost for free. And string theory reaches further still. It aims to unify all four forces of nature into one framework, a single description of everything. The second program is called Loop Quantum Gravity, and it takes almost the opposite path. Instead of unifying all the forces, it focuses on space-time itself. It proposes that space is not smooth and endlessly divisible the way it looks. Instead, at the tiniest possible scale, space-time comes in discrete chunks, woven together like a fabric of tiny loops. Zoom in far enough, and the smooth stage on which everything plays would break into grains. Loop quantum gravity does not try to unify gravity with electromagnetism or the nuclear forces. It simply asks what happens if you take Einstein's geometry and cut it into quantum pieces. Here is the uncomfortable truth. These two programs are considered largely incompatible by the very physicists who work on them. They start from different assumptions, they picture reality in different ways, and after decades of effort, no one has proven either one correct. A handful of researchers have tried to braid elements of both into hybrid ideas, but there is no agreement, no finish line in sight. The two grandest attempts to explain what gravity is made of cannot both be right, and possibly neither is, which brings us to the question hiding at the bottom of all of it. What if gravity does not have a particle at all? What if asking for the graviton is like asking what colour the number 7 is? A question that sounds reasonable but rests on a mistake. Remember that in general relativity, gravity is not a thing travelling through space. It is the shape of space. When the Earth circles the Sun, nothing reaches out to grab it. The Sun has simply pressed a deep curve into space-time, and the Earth rolls along the inside of that curve, following the straightest possible path through bent geometry. If that picture is the final truth, then gravity is not a force with a messenger. It is scenery, and you cannot bottle scenery into a particle. Some physicists suspect that treating gravity as a field with a particle may be a category error, a way of forcing geometry to wear a costume that does not fit. Others are certain the graviton must exist, because everything else in nature is quantized, and it would be strange for gravity alone to stay smooth while the rest of reality comes in lumps. Nobody knows. That is the honest answer. The single most familiar force in your life, the one holding your feet to the floor at this very second, may or may not be built from a particle, and the disagreement runs to the foundations. What makes this stranger still is how much we can do around gravity while remaining blind to its smallest piece. Consider what human beings have already achieved. We took a picture of the shadow of a black hole, not nearby, not next door, but Sagittarius A star, the giant black hole at the center of our own galaxy. sitting about 27,000 light-years away. We captured the ring of glowing gas bent around a place where gravity is so intense that light itself cannot climb out. We measured that ring to a precision like spotting a donut resting on the surface of the moon. We have listened to two black holes collide more than 1 billion light-years off and felt the tremor in detectors here on Earth. And in all of that, in every triumph, we have never once caught the single particle that gravity may be built from. We can photograph gravity's most violent handiwork across the width of the galaxy, yet the humblest brick of the force, if it is a brick at all, has slipped past every net. That is the peculiar shape of our ignorance, not blindness exactly. More like knowing a language fluently while having no idea what its letters are made of. So the graviton hunt goes on, in a lab where a small drum floats in frictionless helium, chilled to the edge of absolute zero, waiting through the long silence for one faint click that may never come. Freeman Dyson's warning still hangs over the whole enterprise, that gravity at the single particle level is so absurdly faint it seems built to hide. Maybe the click arrives one quiet night and rewrites the textbooks. Maybe it never does, and we slowly come to accept that gravity was never a particle, only the bending of the stage everything else dances upon. Either way, the mystery does not soften, it only deepens. Because whether or not gravity has a smallest piece, it does have a limit, a place where its gentle marble in a bowl behavior turns absolute and merciless. Here is insert C, raw narration. For a long time, the question of whether gravity is made of a particle lived only on chalkboards, in equations no experiment could touch. That is starting to change. In laboratories run by Stevens Institute of Technology and Yale University, two physicists, Igor Pikovsky and Jack Harris, have decided to stop treating the graviton as a thought experiment. They are building the first machine ever designed to catch one. And when you look at what that machine actually is, the strangeness of the whole problem comes into focus. You might picture something enormous, a tunnel miles long, a collider ringed with magnets. It is nothing like that. The heart of the detector is small enough to hold in your hand. It is a resonator only about 1 centimetre across, a tiny drum, a slab of matter engineered to ring at a single clean frequency. That is the entire target. Not a wall of sensors, not a field of antennas. One small object tuned to hum, waiting to be struck. To make it sensitive enough, the physicists first have to make it quiet. And quiet here means something far colder and stiller than any silence you have ever known. The resonator is submerged in superfluid helium, a liquid so cold it stops behaving like an ordinary fluid and flows without any friction at all. The whole assembly is chilled to a fraction of a single degree above absolute zero, the lowest temperature that can exist, around 459 degrees below zero on the Fahrenheit scale. At that temperature, the drum is cooled into what physicists call its quantum ground state. It is as motionless as the laws of physics permit. It holds still not because nothing is touching it, but because it has been drained of nearly every last shiver of heat. Now think about why it has to be that cold, because this is where the mechanism becomes almost unbelievable. A gravitational wave is a ripple in space-time itself, a stretching and squeezing of distance, rolling out from some violent event far across the universe. Two black holes collided, or two neutron stars, and the shock travelled outward as a wave in the shape of space. If gravity really is quantized, if it really is built from particles the way light is built from photons, then that wave is not perfectly smooth. It is grainy. It is made of individual gravitons, uncountable numbers of them, each one a single indivisible piece of the gravitational field. The plan is to catch exactly one of them. When a graviton strikes the little drum, in theory it should deposit a single unit of vibration, one quantum of sound, what physicists call a phonon. Not a wave you could feel, not a note you could hear. A phonon is the smallest possible click of vibration a material can hold, one rung on a ladder that cannot be divided any finer. The detector is designed so that the arrival of one graviton nudges the resonator up exactly one rung, from perfect stillness to the faintest possible tremor, and that jump is what the instrument is built to notice. One particle in, one click out. That is the whole idea. You can already sense the problem. The signal is not just small, it is smaller than almost anything humans have ever tried to measure, and it is buried under noise from every direction at once. This is the part that turns the project from clever into nearly impossible. Consider what counts as noise here. A truck passing on a road outside the building shakes the ground, and that shaking would rattle the drum 1,000,000,000,000 times harder than any graviton ever could. A door closing in the hallway, a pump humming 2 rooms away. Even the researchers themselves are a problem. The warmth of a human body, the ordinary heat you radiate just by being alive, is a flood of energy compared to the whisper the detector is listening for. Every stray photon of that heat, every faint vibration carried through the floor, every gust of warm air has to be filtered out, blocked, or subtracted, so that a single click can stand alone and mean something. Everything that makes a laboratory feel like an ordinary room is, to this instrument, a roar. That is the tactile way to hold it in your mind. Imagine standing in the exact center of a hurricane, wind screaming past you from every side, and being asked to listen for one snowflake landing softly somewhere nearby. Not a handful of snow. One flake. You would have to somehow silence the entire storm, hush every gust and every howl, until the only thing left in all the world was the tiny sound of that single crystal touching down. The graviton detector is an attempt to build exactly that silence, out of superfluid helium and temperatures near the floor of the universe, so that one quantum click has room to be heard. And even then, catching the click is only half the trouble. The physicists cannot simply watch the drum. Watching it in the quantum sense would disturb it, because measurement itself deposits energy and jostles the very rung you are trying to read. So the technique has to be gentler than a glance. The detection scheme is designed to sense the change in the resonator's energy without smearing away the delicate state that carries the answer. It is a kind of listening that tries not to touch. The whole art of the machine is in that restraint, in extracting one bit of truth without drowning it in the act of looking. Here is where honesty matters. As of early in the year 2026, this detector is still under construction. It is not finished. It has not run. No graviton has ever been directly detected, not by this instrument, not by any instrument anywhere, not once in the history of physics. This is the frontier as it actually stands, a device being assembled piece by piece, a bet that the smallest tremor in the coldest object ever built might one day carry a message from the grainy structure of gravity itself. It may work. It may reveal nothing for years. That uncertainty is not a flaw in the story. It is the story. And there is an old warning hanging over the whole effort, one that makes you appreciate just how bold this attempt is. Decades ago, the physicist Freeman Dyson worked through the numbers on what it would take to reliably catch a single graviton using conventional methods. His conclusion was almost a joke, except that it was serious. He calculated that a detector built the straightforward way, made massive enough and dense enough to have a real chance of stopping one graviton, would have to be so heavy that it would collapse under its own gravity and become a black hole before it ever registered a thing. The very act of building a big enough net would crush the fisherman. That was Dyson's way of showing, in one grim image, how absurdly faint gravity's quantum signal is. It is so weak that the naive path to measuring it destroys itself. What the Stevens and Yale teams are attempting is a way around that trap. Not a bigger detector, but a colder, quieter, cleverer one. Instead of trying to physically block a graviton with sheer mass, they are trying to sense the single click it leaves behind in an object tuned to notice nothing else. It is the difference between building a wall thick enough to stop a raindrop and building an ear delicate enough to hear one land. Whether that cleverness is enough to beat Dyson's warning is a question no one can answer yet because the machine has not spoken. But you can see now why this belongs in the middle of the larger puzzle. All the talk of whether gravity is a particle or a shape, all the theories and the equations comes down in the end of this small drum, floating in frictionless liquid at the edge of absolute zero, waiting for a knock that may never come. This is the actual engineering behind the abstract question, not a metaphor. Real helium, real cold, real vibration, a real attempt to hold gravity still enough to hear its smallest possible voice. And the fact that the best minds in the field have to work this hard, chill matter this deeply, and filter the world this completely, just to have a chance at detecting one, graviton tells you something on its own. It tells you the thing they are hunting is either impossibly faint or not quite a thing at all. That is the quiet edge the whole search now sits on. We have designed the trap. We have poured the cold. We have imagined the single click. And still nothing has ever clicked. After all the effort, the deepest answer remains open, and it points in a direction that unsettles even the people building the detector. So gravity may not be a particle at all, and to see it at its most extreme, you have to go somewhere it stops being gentle, to a place where it becomes a door that only opens one way. So gravity may not be a particle at all, and to see it at its most extreme, you have to go somewhere it stops being gentle, to a place where it becomes a door that only opens one way. That door has a name in physics. It is called escape velocity, and it is a plain idea before it becomes a terrifying one. Escape velocity is simply the speed you need to break free of something's gravity and never fall back. Throw a ball upward and it slows, stops, and returns. Throw it faster and it climbs higher before it returns. Throw it fast enough and it never returns at all. That threshold speed depends on only two things. It depends on the mass of the world you are leaving and on how far you start from its center. Nothing else. Not the size of the ball, not its color, not how it is thrown. For Earth, that magic number is about 25,020 miles per hour. Reach that speed pointed away from the ground and Earth can never pull you back. That is why rockets are so violent. They are chasing a number carved into the shape of the planet itself. Before we go further, if this is the kind of thing that quiets your mind at night, a like or a subscribe helps this channel more than you would guess. We are also on Spotify if you prefer to listen in the dark. That is the only time we will ask. Now hold that number in your hand and change the world underneath it. The Sun is far more massive than Earth, so its grip is far stronger. To leave the surface of the Sun, you would need to move at roughly 1.37 million miles per hour. The same rule, the same simple relationship, just a heavier world doing the pulling. Make the world heavier still, or squeeze it smaller, and the acquired speed climbs and climbs. And here is where the idea turns into something stranger than any story. Escape velocity has no ceiling written into it. It just keeps rising as gravity gets more intense. So ask a quiet question. What if you compressed a world so tightly that its escape velocity reached the fastest speed there is? What if the number climbed all the way up to the speed of light? Light travels at about 670.6 million miles per hour. That is the universal speed limit, the ceiling that nothing with mass can ever reach. And gravity, if you concentrate it enough, can demand exactly that price to leave. Take our own planet as the example, because the number is almost impossible to believe. Earth already holds you down with familiar weight. Now imagine keeping every ounce of Earth's mass, every mountain, every ocean, every person, but crushing all of it into a ball just 9 millimeters across. That is roughly the size of a peanut. At that density, Earth's escape velocity would equal the speed of light. To leave the surface of that peanut, you would have to travel as fast as light itself, which nothing can do. Squeeze any object past that point, and you have made a black hole. That is all a black hole truly is. It is matter compressed past its own escape point. So a black hole is not a cosmic vacuum reaching out to grab you. It is not a hole in the ordinary sense. It is a place where gravity has become so concentrated that the speed you would need to escape has crossed above the speed of light. and since nothing can move faster than light, nothing can climb back out. Not a rocket, not a signal, not light itself. The trap is sealed by a speed limit built into reality. The boundary around that trap has a name too. It is called the event horizon. The event horizon is not a surface you could touch. It is not a shell of anything solid. It is simply the exact line in space where escape velocity equals the speed of light. On the outside of that line, escape is merely very hard. On the inside, escape would require moving faster than light, and relativity is blunt about what that would cost. To push any object with mass all the way up to light speed would take an infinite amount of energy. Not a lot of energy. Infinite. A quantity that does not exist and cannot exist. So the rule inside the horizon is absolute. There is no engine powerful enough, no burst of force clever enough, no future technology imaginable that could ever pull something back across that line. Once matter crosses the event horizon, it is gone from the outside universe forever. Once light crosses it, that light will never reach another eye. Even information, the pure record of what a thing was and where it went, has no physical path back out. The event horizon is a one-way door. And the strangest part is what that door feels like when you reach it. You might expect a wall. You might expect a flash, a jolt, some violent announcement that you have arrived at the edge of everything. There is none of that. If you fell toward a large enough black hole, you would cross the event horizon and feel absolutely nothing unusual in that instant. There is no barrier there. There is no membrane, no shimmer, no sound. The space at the horizon looks exactly like the space just outside it. It is ordinary emptiness. It just happens to be the last emptiness you will ever be able to leave. Think of it as a door with no handle on the far side. You walk through, and the door does not slam. It does not even close, because there was never anything there to close. You simply notice, if you could still do anything about it, that every direction you might travel now leads deeper in, toward the center. Inside the horizon, the way out is not blocked. It has stopped existing as a direction you can point to. That is a gentler horror than a wall, and a far deeper one. But gentleness is not the whole story, because on the way in, gravity has one more thing to do to you. It has to pull, and near a small dense black hole, one made from the collapsed core of a dead star, the pull is not even across your body. Gravity weakens with distance, and it weakens sharply when the source is small and fierce. So if you fell in feet first, your feet would be measurably closer to the center than your head. Closer means pulled harder, much harder. Your feet would be yanked downward faster than your head. Physicists gave this its own grim name. They call it spaghettification, and the word is not a joke. It is a precise description. The gravity on your lower half would so overwhelm the gravity on your upper half that your body would begin to stretch, not bend. Stretch lengthwise, drawn out like a thread being pulled from both ends. You would be pulled thinner and thinner, drawn into a single long strand of matter, narrower than a strand of spaghetti, long before you ever reached the true center. Around a small black hole, this stretching would begin even before you crossed the event horizon. The door would take you apart on the way through, and what waits at the centre past all of this is the deepest unanswered question of all. General relativity, the theory that predicts everything you have heard so far, follows its own equations inward and arrives at a point it calls the singularity. There, the theory says, all the mass is crushed into a place of zero size and infinite density. Infinite. And that is exactly where physicists grow quiet, because infinity is usually not an answer. It is usually a signal. When a theory hands you infinity, it is often telling you that the theory itself has stopped working, that it has been pushed past the edge of what it can describe. Most physicists do not believe there is truly a point of infinite density inside a black hole. They believe there is something we do not yet understand, and that a deeper theory, one that finally unites gravity with the quantum world, will replace that infinity with something real. There is a second unsolved knot too, and it lives at the horizon rather than the centre. It is called the information paradox. Quantum mechanics insist that information about the world can never be truly destroyed. Yet the event horizon seems to swallow information completely, sealing it away where it can never affect anything again. Those two ideas cannot both be fully right, and reconciling them has occupied some of the sharpest minds in physics for decades. As of now, the paradox remains open. We know the door only opens one way. We do not yet know what that means for the deepest laws of reality. Sit with the whole picture for a moment. A black hole is not exotic in its recipe. It is only gravity. The same gravity holding you in your chair right now, taken to the limit where its own escape velocity crosses the speed of light. Squeeze anything small enough and it happens. A peanut-sized Earth, a collapsed star. The rule never changes, only the density changes, and past a certain density the door appears, silent and handleless, and the fastest thing in existence, light, discovers it has run out of exits. That is what it means for gravity to become a one-way door. It does not roar. It does not warn you. It simply arranges space so that leaving is no longer among the things that can happen. And yet, for all its finality, this trapping of light is not even gravity's most delicate trick. For a long time, all of this lived only in equations. A boundary you could describe but never look at. A darkness defined by mathematics and nothing else. Then, in April of 2019, that changed. A team of astronomers released a single image, and for the first time in history, you were looking at the shadow of a real black hole. They called the object M87 star the supermassive black hole at the centre of a galaxy named Messier 87. It is not a modest thing. Its mass is about 6.5 billion times the mass of our Sun, all of it folded into a single point of collapse. And it is far away, so far that the number almost stops meaning anything. The light in that photograph left its source around 53 million years ago, and it crossed 53 million light years of empty space before anything on Earth caught it. To capture something that distant and that dark, no single telescope would ever be enough. So the astronomers built one that spanned the planet. It was called the Event Horizon Telescope, and it was really a network, a chain of radio dishes scattered across the world, from mountain tops in Chile to the ice at the South Pole. By linking them together and letting the Earth turn beneath them, they stitched their separate signals into one. In effect, they created a virtual telescope as wide as the planet itself, an eye the size of the world, pointed at a single smudge of shadow at the core of another galaxy. Before we go on, if this is the kind of thing that quiets your mind at night, a like or a subscribe helps more people find these. We are on Spotify too, if you would rather listen with your eyes closed. That is the only time we will ask. Now look at the picture itself, because it is easy to misread. What you see is a ring of fire, a soft, uneven donut of orange light with a hole of pure black at its centre. Your first instinct is to think the glowing part is the black hole. It is not. The black hole is the darkness in the middle. That central shadow is the one thing in the image giving off no light at all, the place where light checks in and never checks out. The bright ring is everything falling toward it. It is gas and dust and the shredded remains of stars, spiraling inward and heating up as they crowd together. Near the edge of a black hole this size, that material is torn along at a fair fraction of the speed of light and cooked to temperatures that make it blaze in radio waves. So the fire is real, but it is the last glow of matter on its way down, not the thing swallowing it. And here is the part that should stop you for a moment. The ring is not only matter you're seeing, it is also light that has been bent. Gravity this strong does not just tug on light, it steers it, curving the paths of nearby rays until some of them wrap partway around the black hole before flying off toward you. So a portion of that orange halo is the glow from behind the hole and beside it, gathered up and folded around into a circle. You are looking at light that took the long way, dragged around a dark mass so heavy it curls the rays back on themselves. The shape of the ring is the shape of gravity itself drawn in fire. That first image was of something in a galaxy far outside our own. But 3 years later, in May of 2022, the same worldwide network turned its attention closer to home and released a second portrait. This one was of Sagittarius, a star, the supermassive black hole at the centre of our own Milky Way. It sits about 27,000 light years away, in toward the crowded heart of the galaxy in the direction of the constellation Sagittarius. For all of human history it had been hidden behind thick clouds of dust and gas. Now, at last, there was a picture of the monster we quietly orbit. Sagittarius. A star is smaller than M87 star, at least in raw mass. It weighs in at roughly 4 million times the mass of the Sun. That is still an unimaginable amount. 4 million suns pressed past their own limit, but it is far less than the 6.5 billion at the core of Messier 87. It is also much closer to us, which is the only reason we can see it at all. To photograph its shadow, the astronomers had to resolve a ring of light, just 52 millionths of a single arc second across. It is worth sitting with how small that angle is. An arc second is already a tiny slice of the sky, 1/3600th of a degree. This ring was measured in millionths of one. The team offered a comparison that lands the point. It was like standing in your own backyard and trying to photograph a donut resting on the surface of the moon. A glowing donut, 250,000 miles away, and you are asked to catch it clearly enough to measure the hole in its middle. That is the precision it took to see the thing that anchors our galaxy. Now hold the two images side by side, because they hide a quiet trick of scale. In their respective photographs, M87 star and Sagittarius. A star look like similar objects. Both are rings of orange light around a dark centre, and both appear to take up about the same little patch of sky. You would guess they were roughly the same size. They are not even close. M87 star is the giant. It is around 1/600 times more massive than Sagittarius A star, and physically its dark heart is vast enough to swallow our entire solar system with room to spare. Its shadow could hold the orbit of every planet around the Sun and keep going far beyond. Sagittarius. A star, by contrast, would fit comfortably inside the orbit of Mercury. One of these is more than 1,000 times the bulk of the other, and yet on film they were nearly the same size. The reason is distance, working as a great equalizer. M87 star is roughly 1,600 times heavier, but it is also proportionally much farther away, some 2,000 times more distant than the black hole in our own galaxy. Being larger makes it look bigger, being farther makes it look smaller, and those two effects very nearly cancel. It is the same reason the sun and the moon appear almost identical in your sky, though one is 400 times wider than the other and 400 times more distant. So the cosmos handed us two black holes at opposite extremes of size and framed them at just the right distances to make them twins. There is one more thing worth holding on to about both of these portraits. Nobody actually saw the black holes. That is not how it works, and it never will be. The dark circle at the center of each image is a region giving off nothing you could ever collect. What was photographed in both cases was the silhouette, the absence, a round patch of pure black outlined by everything bright enough to be caught falling in around it. We did not take a picture of the object. We took a picture of the hole it leaves in the light. And that outline is not a fuzzy guess. Its size in each image matches what the equations predicted for a boundary at exactly that mass. A boundary set precisely where the escape speed climbs to the speed of light. The math had described that edge for a century. Now there were two photographs of it, dated and measured, one in a galaxy 53 million light-years off, one at the middle of our own. The point of no return had been sketched in fire twice, and both times it fell right where the theory said the door would be. So these are not abstractions anymore. When you picture a black hole tonight, you can picture two specific ones with real names and real numbers. M87 star, 6.5 billion suns, its light 53 million years old. Sagittarius A star, 4 million suns, sitting 27,000 light-years toward the heart of the Milky Way, small enough on the sky to be a donut on the moon. Two dark circles ringed in bent light. Two doors photographed from the outside, both sealed in a way nothing has ever undone. The same gravity that seals that door shut also does something gentler and just as strange, because long before it traps light, it bends it, and it bends time along with it. The same gravity that seals that door shut also does something gentler and just as strange, because long before it traps light, it bends it, and it bends time along with it. Light does not fall the way a stone falls, yet it does not travel in a perfectly straight line either. When a beam of starlight passes close to something massive, a galaxy, a cluster, a black hole, its path curves. The mass does not reach out and grab the light. The mass bends the space the light is crossing, and the light simply follows the shape of that space. Astronomers call this gravitational lensing, and it is one of the clearest fingerprints gravity leaves on the sky. Before you settle in, if this quiet kind of physics is what you came for, a like or a follow helps more people find these long nights, and you can find the same voice on Spotify. That is the whole ask. Now, let the sky do the rest. Einstein worked out the mathematics of this bending in 1915 in the same theory that reimagined gravity as warped geometry. The idea sat in the equations for years before anyone drew out its strangest picture. By 1936, Einstein described what happens when a distant object sits directly behind a massive one, perfectly aligned with your line of sight. The light from the hidden object gets wrapped around the closer mass in every direction at once. Instead of a single point, you see a complete circle of light. That circle is now called an Einstein ring. An Einstein ring looks, in a deep image of the sky, like a glowing halo of smeared and duplicated light. The galaxy making that light is invisible to you. It is tucked directly behind the object doing the ending, completely hidden. What you actually see is only its light, dragged around the foreground mass and stretched into a ring. The source is one thing. The image is a circle. Gravity did that, and gravity alone. This is not a curiosity that astronomers file away and forget. Lensing has become a tool. Because the amount of bending depends on how much mass is present, you can measure the mass by measuring the bend. And when the bending is far stronger than the visible stars and gas can explain, it tells you there is mass you cannot see. That is how lensing helps map dark matter, the invisible material that outweighs ordinary matter across the cosmos. You watch how it warps the light of galaxies behind it, and you trace the shape of something that gives off no light at all. Lensing also measures distances across the universe, turning the bending of a beam into a ruler. So gravity bends light. Hold that, because it does something to time that is even harder to accept, and you rely on it every single day. Time does not run at one fixed speed everywhere. It runs slightly faster where gravity is weaker, and slightly slower where gravity is stronger. This is not a feeling or an illusion. It is measured constantly by the satellites that tell your phone where you are. There is a clock in your pocket that only works because engineers accepted that gravity distorts time. Consider the GPS satellites overhead right now. They orbit at about 12,750 miles above you, circling the Earth at roughly 8,700 miles per hour. Two different effects pull on their onboard clocks in opposite directions. Because they move so fast, the physics of motion slows their clocks by about 7 microseconds each day. But because they sit so high, In weaker gravity than you feel on the ground, their clocks also run fast by about 45 microseconds each day. Add those together and each satellite's clock gains about 38 microseconds per day compared to a clock on the surface. 38 microseconds sounds like nothing you would ever notice. A microsecond is a millionth of a second. But GPS finds your position by timing signals that travel at the speed of light, and light covers about 1,000 feet in a single microsecond. If the system ignored these effects, the errors would not stay small, they would pile up. Within a single day, your location would drift off by several miles. The little blue dot that keeps you on the right road would wander clean off the map by morning, so the correction is baked in. The satellites are built to tick slightly slow on the ground, so that once they are in orbit, in weaker gravity, they tick at the right rate for us. Every time your phone quietly finds itself, it is trusting Einstein's equations about warped time. You are relying on gravity slowing time down, and you never feel a thing. That is gravity as you meet it in daily life, bending light in the deep sky and reshaping time above your head. But to see how violent it can become, you have to leave the gentle end entirely and listen to two black holes colliding. On the 14th of September 2015, two enormous detectors in the United States felt the ground of reality shiver. One sat in Louisiana, the other stood far away in Washington state. They are called LIGO, and each one is built around two arms, each arm about 2.5 miles long, with laser light bouncing down them and back. For 100 years, one prediction of Einstein's theory had gone unconfirmed. He had said that when massive objects accelerate violently, they should send ripples out through space-time itself, waves in the fabric of space spreading at the speed of light. Almost no one thought a ripple like that could ever be measured on Earth. What the two detectors caught, within thousandths of a second of each other, was exactly that ripple. Its source was two black holes, one about 29 times the mass of the Sun, the other about 36 times, spiraling into each other and merging into one. That collision had happened about 1.3 billion light-years away. The wave it made had been travelling toward us for 1.3 billion years, crossing the emptiness at light speed until it finally washed over Louisiana and then Washington and stretched their arms by the tiniest measurable amount. A century-old prediction, confirmed in a fraction of a second. Now hold the numbers together, because this is where it stops making ordinary sense. In the final moment of that merger, the collision poured out energy as gravitational waves at a staggering rate. For that fraction of a second, it radiated roughly 50 times more power than the combined light of every star in the entire observable universe. Every star in every galaxy you could ever see, all of them shining at once, and this single silent collision briefly outshone all of it, not in light, but in the pure shaking of space. And yet, by the time that unimaginable wave reached the detectors, it was almost nothing. It stretched and squeezed LIGO's 2.5-mile arms by less than 1/10,000th of the width of a single proton. A proton is already far too small to see. This was a fraction of that, spread across miles of steel and laser. Picture space itself squeezed thinner than a single atomic nucleus across the whole length of the detector arm. A whisper of a change buried in the machinery and yet real enough to record. The most powerful event ever measured arrived as the faintest tremor ever measured. No human sense could ever register that. There was no sound, no shudder you could feel, no flicker of light, and that is the point. Until this moment, everything we knew about the universe came from light of some kind. Visible light, radio, X-rays, all of it a form of light. This detection did not use light from the collision at all. Black holes merging give off no light. They only shake space-time. LIGO had learned to feel that shaking directly. It opened an entirely new way of studying the sky, called gravitational wave astronomy, a way to hear cosmic collisions that shine with no light whatsoever. For the first time, we could listen to the dark. So gravity, at its most extreme, is strong enough to make the universe ring like a struck bell. And to understand where that strength lives, you have to look at the densest ordinary objects that exist, the collapsed cores of dead stars. A neutron star is what remains when a giant star burns out and its core falls in on itself. Picture something only about 7 miles across. That is a distance you could drive in a few minutes on an open road. Now pack into that tiny ball up to twice the entire mass of our Sun. The Sun is over 860,000 miles wide. Squeeze nearly that much material, sometimes more, down into a sphere the size of a city, and you get a neutron star. The gravity at its surface is almost beyond comparison. It is roughly 100 billion to 200 billion times stronger than the gravity you feel standing on Earth right now. That number is so large it stops meaning anything, so hold it a different way. The escape velocity from a neutron star's surface, the speed you would need to leave it forever, is more than half the speed of light. Not half the speed of a rocket. Half the speed of light itself, over 90,000 miles per second, just to climb off the surface of a ball 7 miles wide. The matter inside is crushed past anything you could hold. Atoms cannot keep their ordinary shape under that pressure. Their structure is squeezed away until the material is packed almost solid with neutrons. A single teaspoon of neutron star matter, scooped out and somehow brought here, would weigh about as much as a mountain. One small spoonful, heavier than a peak of rock, or as much as a large ocean liner. That is not a trick of wording. It is the direct result of gravity compressing matter until the empty space inside atoms is gone. Sit with what that tells you about this one force. The same gravity that gently bends a distant beam of starlight, that quietly runs the clocks in your phone a few microseconds slow, is also the thing that can take the core of a star and crush it into a spoonful heavier than a mountain. It is the thing that can wrap light into a perfect ring, and the thing that can shake the whole fabric of space until detectors on Earth feel a tremor thinner than a proton. One force, every scale. All of it proven, all of it measured, none of it guessed. And every piece of it has been checked. The bending of starlight is photographed. The slowing of time is corrected for in orbit every day, or your navigation would fail. The ripples in space-time have been caught by machines miles long, The crushing gravity of neutron stars is written in their light and their spin. This is not a story about what gravity might do. It is a record of what it does, again and again, exactly as the equation said it would. You would think a force that can do all of this, bend light, slow time, ring space-time like a bell, and crush a star into a city-sized ball, would be the strongest thing in nature. You would think it would tower over everything else. That is the natural assumption, and it feels almost obvious after everything you have just seen. And here is the part that should stop you cold. Because this force that bends starlight and stretches time is, measured against the others, almost nothing at all. And here is the part that should stop you cold. Because this force that bends starlight and stretches time is, measured against the others, almost nothing at all. Gravity is the weakest of the four fundamental forces, not slightly weaker, not weaker by a comfortable margin you could picture. Compare the pull of gravity between two electrons to the electric force between them, and gravity comes in about 10 to the 47th power times weaker. Write that out and it is a 1 with 47 zeros behind it. That is the ratio. That is how faint the thing holding you to your bed really is. Take a moment with that number, because it is easy to read and impossible to feel. If you enjoy sitting with ideas this strange, a like or a subscribe helps this channel keep making them, and these scripts live on Spotify too. Now let the count settle back over you. Between an electron and a proton, the gap narrows a little, to roughly 10 to the 39th times weaker. Still a number with no home in ordinary experience. And yet gravity is the force that runs the universe. It shapes galaxies. It lights stars. It decides the fate of everything large. The weakest force wins at the biggest scale, and understanding why is the first strange thing about it. The answer is not that gravity is secretly strong. The answer is that gravity never quits. Electric charge comes in two kinds, positive and negative. Put them together and they cancel. A block of matter is made of enormous electric forces, but the pluses and the minuses balance so precisely that the block sits there electrically quiet. Gravity has no minus sign. Mass only ever attracts. There is no anti-mass to set against it, nothing to cancel the pull, so gravity never balances out. Every speck of matter in a star adds its tiny share, and none of it subtracts. Add up enough, almost nothing, with unlimited range and no cancellation, and you get the force that holds a galaxy together. That is the trick of it. Electromagnetism is far stronger, but it is forever tripping over its own opposite charges. Gravity is feeble and relentless wins the long game. Still, none of that explains the weakness itself. Why should the force be so faint to begin with? This is one of the deepest open wounds in physics, and it has a name. Physicists call it the hierarchy problem. Line the forces up by strength, and gravity does not sit a step below the others. It sits far, far down, roughly 10 to the 24th to 10 to the 40th times weaker than the rest, depending on how you frame the comparison. The theories that describe the other forces so beautifully, the mathematics of quantum fields, expect gravity to be enormously stronger than we ever measure. The prediction and the world disagree by a gap so vast it looks less like an error and more like a message we cannot yet read. No one has an accepted answer. There is no equation on a board somewhere that closes the case. There is only the question, sitting where it has sat for decades. Why is gravity so absurdly, so specifically weak? There is one idea that many physicists find beautiful, and it is worth telling slowly, though you should hold it lightly because it is proposed and unconfirmed. The idea is that gravity is not actually weak at all. The idea is that it leaks. Imagine that the 3 dimensions of space you move through are not the whole of space. Imagine there are extra dimensions, folded up small or hidden in ways your senses can never reach. The other forces, in this picture, are stuck to our familiar 3 dimensions. They cannot leave, but gravity can. Gravity spreads into the hidden dimensions too, and by the time it reaches you, it has been thinned out, diluted across a larger space than you can perceive. Picture water poured onto a fine mesh. Most of it slips through the tiny holes and vanishes below, and only a faint trickle stays on the surface where you can see it. In this idea, gravity is that trickle. The full strength drains away into dimensions you cannot see, and what remains, the part pinning you gently to the floor, is only the leftover film on top of the mesh. The force feels weak because most of it has gone somewhere you can never look. This is not one lonely notion. It has been worked out in careful detail. In 1998, 3 physicists, Nima Arkani-Hamed, Savas Dimopoulos, and Gia Diwali, published what is now called the ADD model, which proposed exactly this kind of leaking into large extra dimensions. A year later, in 1999, Lisa Randall and Raman Sundram offered a different version, with an extra dimension that is curved rather than flat, warping the strength of gravity across it. Both are serious, respected proposals. Neither has been confirmed. No experiment has caught gravity slipping into a hidden dimension. The idea remains a candidate answer to the hierarchy problem, elegant and unproven, waiting for evidence that may never come. So the weakness has no settled cause. And here is the next strange thing about this force, a property that sets it apart from everything else. You cannot block it. Think about how you shield yourself from the other forces. You step behind a wall to escape the wind. You wrap a wire in a metal cage and the electric field outside dies away, because the charges in the metal rearrange to cancel it. Radios go quiet inside an elevator. Magnetic fields can be steered and trapped and shielded. Every force you meet in daily life can be blocked by putting the right material in the way. Every force but one. Gravity cannot be shielded by anything. There is no material, no wall, no chamber, no clever arrangement of matter that will cast a gravitational shadow. And the reason goes back to that missing minus sign. Shielding works because charge has an opposite. Slide negative charges toward the field, and they cancel the positive, and behind them the field is gone. Mass has no opposite. You cannot bring negative mass to the wall, because as far as anyone has ever found, negative mass does not exist. So there is nothing to cancel with. Every ounce of matter you put between yourself and a planet adds its own pull. It does not subtract. Try to build a gravity shield and you have only built more gravity. You should be careful here, because this is exactly the kind of gap where wishful stories grow. Over the years, there have been laboratory claims of gravity shielding, most famously involving spinning superconducting disks said to lighten objects held above them. It is worth saying plainly, those claims have never been successfully replicated, and physicists broadly regard them as not real. They are not a live possibility waiting for funding. They are a debunked hope. Gravity, as best as anyone has ever been able to test, cannot be turned off, cannot be blocked, cannot be hidden from. It reaches through the entire mass of the earth beneath you, and it never once lets go. And that leads to the strangest question of all, the one that sounds like science fiction and turns out to touch real observations. If gravity only ever attracts, if there is no minus sign, then is there anywhere in the universe that gravity seems to push instead of pull? Is there any such thing as anti-gravity? The honest answer is that there is exactly one whisper of it, and it fills the sky. The universe is expanding and its expansion is speeding up. Something is driving galaxies apart faster and faster, working against the inward pull of all the matter there is. Physicists call that something dark energy, and it behaves on the larger scales like a gravitational repulsion. It is the closest thing to anti-gravity that anyone has ever observed. Not a machine, not a trick, a property of empty space itself, gently pushing the cosmos open. But hold your excitement, because this is not a force you could ever bottle. Dark energy acts only across enormous cosmic distances, stretching the gaps between galaxies. It cannot be harnessed, cannot be studied up close, cannot even be explained. No one knows what it is. It is written into our best measurements as a fact we cannot account for, the one place in nature where gravity or something like it appears to reverse. And in 2025 that mystery grew stranger still. A project called DESY, the Dark Energy Spectroscopic Instrument, set out to map the universe in 3 dimensions with extraordinary care. It charted more than 18 million galaxies, quasars, and stars, 18.7 million objects, plotting the shape of cosmic expansion across billions of years. And the data hinted at something no one expected. Dark energy might not be constant. It might be weakening over time. The push that opens the universe may have been stronger in the past and fading now. If that were confirmed, it would rewrite the future of everything. But it is not confirmed, and this is where you must be patient the way physicists are forced to be. The hint sits at a statistical strength of about 3.2 to 3.4 sigma. In physics, a real discovery is not called until the evidence reaches 5 sigma, a much higher bar meant to guard against flukes and hidden errors. 3.3 sigma is suggestive. It is intriguing. It is worth every telescope pointed at it. But it is not settled, and it may yet melt away as more data arrives. So hold it as a question, not an answer. Dark energy, the one whisper of repulsion in a universe of pull, may be changing, and we do not yet know. Now step all the way back and look at what gravity actually is. Once you stack these strange facts on top of each other, it is the weakest force by a margin no one can fully explain. It cannot be shielded by any material ever found. It only attracts, never balances, and so it quietly rules the largest structures in existence. Its one hint of an opposite fills the whole sky, and cannot be touched or understood. And after all of that, we still do not even know its strength to real precision. That last part is almost funny in a quiet way. The number that sets how strong gravity is, the one that sits in Newton's equation, and in Einstein's too, is called Big G. Henry Cavendish first measured its effect in a garden shed in the 1790s, with lead balls and a delicate twisting wire, in an experiment so sensitive that the warmth of his own body could spoil the reading. More than 2 centuries later, with lasers and vacuum chambers and every advantage he never had, the best laboratories in the world still cannot agree on the value. Their finest measurements disagree by a few hundred parts in a million. A 2026 remeasurement still sat about 0.02% away from the earlier reference figure. Big G remains the least precisely known of all the fundamental constants of nature, and no one is certain why. Think of that the next time you set something down on a table. You are watching the oldest force we ever named, the first one written into physics, the one you have felt every second you have been alive, and it is still the one we understand the least. A fridge magnet on your kitchen door lifts a paperclip and beats the entire mass of the planet beneath it, and that little snap of metal is a demonstration, right there in your home, of how faint gravity truly is. The weakest thing in the universe holds the universe together and cannot be blocked and cannot be fully measured, and shows one changing whisper of a push we cannot name. There is a quieter argument underneath all of this, and it has been running for more than 2 centuries. It is not about what gravity does. It is about exactly how strong it is. That number has a name. Physicists call it Big G, the gravitational constant, the single figure that sets the strength of the pull in both Newton's equation and Einstein's. And here is the strange part. It is the least precisely known fundamental constant in all of nature. We have measured the mass of the electron and the frequency of atoms to breathtaking accuracy. Gravity's own strength, the oldest force ever described, remains stubbornly blurry. The story begins in a garden shed in England, in the winter of 1797 and into 1798. A wealthy, painfully shy scientist named Henry Cavendish set out to do something no one had ever done. He wanted to weigh the pull of gravity directly, on a table, in a room. His instrument was almost absurdly simple. A slender wooden rod hung horizontally from a thin wire, like a tiny seesaw dangling by a thread. On each end of the rod sat a small lead ball weighing about 1.6 pounds. Nearby he positioned 2 far larger lead spheres, each weighing roughly 348 pounds. Then he waited. The heavy spheres tugged gently on the small ones. The rod turned just slightly, twisting the wire. By measuring how far it turned, Cavendish could measure the faint attraction between the lead balls themselves. He was for the first time in history watching gravity work between two objects you could lift and hold. The force was so tiny that almost anything could ruin it. A breath of warm air moving through the shed, the heat of his own body leaning too close, a faint draft under the door. Any of these could nudge the wire and drown the signal he was hunting. So Cavendish sealed the apparatus in a case and watched it from another room with a telescope, careful not to warm the air around it. Picture that wire, thinner than a hair in its sensitivity, trembling at nothing more than a stray current of warm air in a silent room. That trembling was gravity, made visible at last. His result was astonishingly good for the time, and you might expect that after 230 years, with lasers and vacuum chambers and atomic clocks, we would have sharpened his answer into something exact. We have not. That is the part almost no one outside physics knows. The best modern laboratories, using methods Cavendish could never have dreamed of, still disagree with each other about the value of big G. Not by a rounding error. Different high-precision experiments produce numbers that clash by up to 550 parts per million. In a field where other constants are pinned down thousands of times more tightly, that gap is enormous, and a fresh remeasurement in 2026 landed about 0.35% away from the accepted reference value, once again refusing to close the gap. The teams are careful, the equipment is superb, the answers still will not line up. Before we go on, a small thing. If you find these quiet, unsolved corners of physics as strange and soothing as I do, a like or a follow genuinely helps this drift keep going, and every episode is on Spotify too if you sleep better with just the voice. That is the whole ask. Now settle back in. So why does the number wobble? Here you have to be careful, because it is easy to reach for something dramatic when the plain answer is more likely. The mainstream view among physicists is not exotic at all. Most believe the disagreements come from systematic errors that have not yet been identified. Something subtle in how each experiment is built, the way a fiber twists over time, tiny thermal shifts, the behavior of the materials, the measurement of the masses themselves. Gravity between small objects is so faint that hidden influences you have not accounted for can quietly bias the result, and every apparatus has its own particular blind spots. That is the leading explanation, and it is the one to hold on to first. There is, however, a smaller and more cautious thought that lingers at the edges. A minority of researchers have not entirely ruled out that something we do not yet understand about gravity itself could be leaking into these measurements. This is very much the aside, not the headline. No respected physicist claims the evidence points that way. But the honest position is that the door has not been fully shut, and part of what keeps people building better torsion balances is the faint chance that the wobble is telling us something real. For now, the working assumption is boring, careful, and probably correct. The number is hard to measure. That is likely all it is. This is the texture of gravity's deeper puzzles. A firm, sensible consensus with a narrow strip of genuine uncertainty running alongside it, and a great deal of discipline required to keep the two apart. You can see the same pattern out at the scale of whole galaxies. When astronomers watch a spiral galaxy turn, the stars at its outer edge move far too fast. By the visible matter alone, those outer stars should trail behind, the way the outer horses on a carousel would fly off if the ride spun too quickly. Instead, the whole disk turns almost together, as if far more mass were present than any telescope can see. The mainstream answer to this is dark matter, an unseen halo of some unknown substance wrapped around each galaxy, adding the extra gravity that holds the fast stars in place. That halo is the consensus, supported by many independent lines of evidence, and it is where the weight of the field firmly sits. But there is a real, if minority, alternative, and honesty requires naming it. It is called modified Newtonian dynamics, or MOND. Instead of adding invisible matter, Mond proposes that gravity itself behaves slightly differently at the very low accelerations found in the outskirts of galaxies. Adjust the law of gravity a little in that gentle regime, its supporters argue, and the flat rotation curves fall out naturally, without any dark matter at all. Most physicists do not accept it as the answer. The dark matter halo explains too many other things that Mond struggles with. But Mond is not a crank idea. It is a serious debated position held by a genuine minority, and it survives precisely because gravity's strength in these faint regimes is so hard to test directly. You get the same discipline when you look at the tiny anomalies inside our own solar system, the little discrepancies that once made headlines. For years, two spacecraft, Pioneer 10 and Pioneer 11, seemed to be slowing down ever so slightly more than gravity alone could explain as they drifted out past the planets. It was a real signal, a whisper of unexplained deceleration, and for a while it tempted people toward new physics. That whisper has since gone quiet. Careful analysis traced almost all of it to a mundane cause. Heat radiating unevenly off the spacecraft themselves gave a gentle push, a thermal recoil that had been underestimated. The Pioneer anomaly is now considered resolved, and it belongs in the settled column, not the mysterious one. One narrow puzzle does remain genuinely open, though it is small. During a handful of spacecraft flybys of Earth, missions like Galileo, Near, and Rosetta showed tiny unexplained changes in their speed, a few fractions of an inch per second that no one has fully accounted for. Later missions did not always show it, which only deepens the strangeness. This flyby anomaly has no confirmed explanation and no identified error, so it stays honestly filed as unsolved. But it is a minor, narrow mystery, a loose thread rather than a crack in the foundation, and no serious physicist treats it as proof that our understanding of gravity is wrong. That is the shape of the whole long argument, and it is worth sitting with. 230 years after a shy man watched a wire twist in a sealed shed, we still cannot agree on gravity's exact strength to better than a few hundred parts per million. We watch galaxies spin too fast and split into camps over whether the missing pull is invisible matter or a bend in the law itself. We chase faint anomalies across the solar system, resolve most of them, and leave a few honestly open. None of it means gravity is broken. Every measurement is close. Every theory works to extraordinary precision, and the disagreements live out at the far decimal places where only the most careful instruments can see them. And yet the number at the very heart of it, the plain strength of the force pressing you into your bed right now, refuses to be pinned down cleanly. The oldest force we ever named is still the one whose exact value we hold most loosely. It is measured everywhere, felt by everyone, and quietly, at the level of pure precision not fully agreed upon by anyone. After more than 300 years, gravity remains the most familiar thing you will ever feel, and the least understood thing physics has ever tried to hold. After more than 300 years, gravity remains the most familiar thing you will ever feel, and the least understood thing physics has ever tried to hold. You have felt it every second of your life. It was there before your first breath, and it will be there when the lights go out and this voice fades. And yet, for all that closeness, no one has ever caught it in the act. No particle to point to, no switch to turn it off, just the quiet, endless pull that keeps you exactly where you are. Think about what that pull might really be. Not a rope, not a hand reaching up through the floor to hold you. According to Einstein, the force pinning you to your bed right now may be nothing more than the shape of space itself, bent gently inward by the simple fact that you have mass. The earth beneath you presses a wide, smooth well into the fabric of space-time, and you are not being yanked downward at all. You're only following the straightest path there is through a geometry that curves. You are resting in the bottom of a bowl you cannot see. That is the strangest part, and it is worth letting it settle. This same shape, this same silent curving of space, is the thing that holds entire galaxies together across 100,000 light years. It is the thing that bends starlight off its path and wraps it into rings. It is the thing that slows time near a heavy world, and the thing that closes over a black hole so completely that not even light, the fastest thing that exists, has ever found a way back out. All of that immensity comes from the weakest force in the universe. Hold both of those truths at once. Gravity rules the cosmos, and gravity is faint almost beyond belief. A small magnet on your refrigerator door lifts a paperclip, and in that instant outpulls the entire mass of the planet beneath it. Compared to the other forces, gravity is trillions upon trillions of times weaker, and no one can fully say why. It cannot be blocked. It cannot be shielded. There is no material, no wall, no box that stops it, because mass only ever attracts and never cancels itself out. It reaches everywhere, forever, and it never lets go. And even now, after more than 2 centuries of the finest instruments ever built, no one has measured its exact strength. Since Henry Cavendish first weighed the pull of gravity with lead spheres and a twisting wire in the 1790s, the world's best laboratories still cannot agree on the number to better than a few hundred parts per million. The most important constant we live inside remains a little blurred at the edges. The force you trust with every step is the one physics still cannot pin down. There is even a faint rumour of its opposite. Out at the largest scales of all, something is pushing the universe apart, stretching space faster and faster, behaving almost like gravity run in reverse. Physicists call it dark energy, the one whisper of anti-gravity anyone has ever found. Recent maps of nearly 19 million galaxies hint that it may be slowly changing over cosmic time, though the signal is still too soft to call a discovery. So even the exception is a mystery. Even the escape from gravity is something no one yet understands. None of this needs to trouble you now. There is no fear in it, only wonder. It is a good thing, in a way, that the most ordinary sensation you know still has a secret at its centre. The weight in your shoulders, the heaviness in your legs, the pull that will soon carry you down into sleep, all of it is warped geometry you will never see and never need to. You do not have to understand it to rest inside it. It has been holding you gently your whole life, and it is holding you still. So feel it, just for a moment, before you drift. Notice the way your body presses into the mattress beneath you. That pressure is not really a downward force at all. It is the shape of space, curved by the earth, and curved a little by you, meeting in the softness under your back. Let your weight sink slowly, the way a marble rolls to the lowest point of its bowl and finally goes still. There is nowhere else for it to go. It has found the bottom, and it rests. You are lying in the deepest, gentlest well there is, the one the whole planet carves beneath you, and you are exactly where that curve wants you to be. Nothing is pulling at you. Nothing is holding you against your will. You're simply following the natural path, the way starlight follows it, the way the moon follows it, the way everything in the sky follows it, quietly, without effort, without end. The force no one can fully explain is the same force tucking you in tonight. It asks nothing of you. It only lets you settle and lets you be still and lets you grow heavier and softer against the bed with every slow breath. Let the wondering go now. Let the numbers and the names loosen and drift. There is nothing left to solve tonight, and nowhere left to fall but into rest. Feel your weight one last time sinking down, held by the shape of space you cannot see. Let it carry you the rest of the way. Sleep well tonight. Good night.